everyone. Welcome to video number 8 of Physics Mechanics. In this video, you're going to learn about energy, work, and power. We will first introduce some examples of energy, and then we will define energy and work together and perform calculations with them. Then we will define power and perform calculations with it. And finally, we will finish off with collisions. In the last video, you learned about a type of collision called an inelastic collision. In this video, we're going to learn about a different type of collision. Let's dive in. There are many types of energy, but they all fall into two categories: potential energy and kinetic energy. Potential energy is the energy of an object due to its position or internal stresses. Kinetic energy is the energy of an object due to its movement. Here are some examples of potential energy. The first is chemical energy, which is energy stored in the bonds between atoms, and it can be harvested with chemical reactions. Chemical energy shows up in a lot of different places. Some examples include food, which we need to survive and move, and firewood, which you can burn to release thermal energy. Then there's nuclear energy, which is energy that is stored in the nucleus of an atom, and it can be harvested by splitting atoms, which is what nuclear power plants do. Gravitational potential energy is the energy of an object due to its height. So in this diagram, an object is hanging above the surface of Earth. When it is released, the gravitational potential energy is going to cause it to fall, and when it does, the energy is going to be turned into kinetic energy. Then there's elastic energy, which is the energy of an object due to internal stresses. An example is when a ball bounces, its shape will be temporarily distorted. So it's going to have elastic energy, which is going to make it want to return to its original shape. And when it does, it can apply a force that causes it to move. Some other examples of elastic energy are when a spring is distorted, its elastic energy is going to make it want to return to its original shape. When a bow is stretched, its elastic energy is also going to make it want to return to its original shape. Then there's magnetic potential energy. You know that magnets attract or repel each other. When two magnets are placed close to each other, they might start moving. So magnetic potential energy is the energy that makes magnets want to move when they are placed close to each other. Now we are getting into kinetic energy. Kinetic energy can be both a broad and specific term. When it's used as a specific term, it's usually used to describe the energy of objects that we think of as being in motion. Examples are an object falling towards the surface of Earth, a car moving, or a baseball that has been thrown. Basically, any objects that can be easily seen as being in motion. Now, some examples of the broad term for kinetic energy are thermal energy, which is the energy of an object due to its temperature. So when an object gets warm, the particles inside it move quicker, and that's basically what thermal energy is. Electrical energy is the movement of electrons. So when a battery is part of a circuit, the electrons move from the negative end of the battery to the positive end, and the movement of those electrons is electrical energy. Sound energy is the vibration of particles. When those vibrations reach your ear, you can hear them. Light energy is the movement of particles called photons. Your eyes work by detecting light that enters them. Now we're getting into work. Work is the application of a force over a distance. The formula for work is force times displacement times cosine of theta, where theta is the angle between the force and displacement. And if the force and displacement are in the same direction, then the work is just force times displacement. Energy is the ability to do work. So, for example, an object that is moving, which means it has kinetic energy. If it collides with another object, then it can do work on that other object by applying a force over a distance. The units for work and energy is joules. The law of conservation of energy states that energy is never created nor destroyed. It can only be converted from one form to another. An important implication of this is the energy of work that is done on an object is the amount of energy it gains. And we can use that implication to find the formula for kinetic energy. So we will start off with the fifth kinematic equation. We're just going to set the initial velocity to 0. And then we divide both sides by 2. Then multiply both sides by the mass. And you know that ma is equal to F, so you can substitute that in to the right side. And now notice that we have force times displacement, which is what work is. And we know that work is equal to the change in energy. So the initial kinetic energy was 0 because we set the initial velocity to 0. So therefore, the formula for kinetic energy is 1/2 times mass times velocity squared. Here's an example of an energy conversion. An object falling to Earth would start at rest at a certain height. So its gravitational potential energy is a certain value, let's just say 100 joules, and it has no kinetic energy because it's at rest. Right before collision with the ground, there is no more gravitational potential energy because the object has no height, and all of the initial gravitational potential energy has turned into kinetic energy. When the object does collide with the ground, the kinetic energy is turned into thermal and sound energy. Using what we just saw, we can find the formula for gravitational potential energy. So we just saw that the initial gravitational potential energy is equal to the final kinetic energy, which is 1/2 mvf squared. So we will go back to a step that we went through when finding the formula for kinetic energy. So we had 1/2 mvf squared equals mad. So this is basically what the formula for gravitational potential energy is. And we will replace some of those variables with different letters. We will replace A with G because G is acceleration due to gravity, which is more specific. We will replace D with H, which is height. So this is the formula for gravitational potential energy. Here is the list of key formulas and concepts. I will be presenting 6 practice problems before moving on to the next concept to help you remember and apply these. Feel free to do as many of them as you want. Here's the first practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. Energy is always conserved, which means that the gravitational potential energy lost is the kinetic energy that is gained. So we can set 250 to the formula for kinetic energy, and we know that the mass is 5. So now we can solve for V and get that it is 10 meters per second. Here's the second practice problem. The solution will come in 3, 2, 1. So we just use the formula work equals force times displacement times cosine of theta, and we plug in all the values to get that the work is 4,330.13 joules. Here's the third practice problem. The solution will come in 3, 2, 1. So the change in kinetic energy is the final kinetic energy minus the initial, and it is equal to the work. So you can solve to get that D is equal to 70 meters. This is an example of negative work, which is basically work that causes an object to lose energy. In this case, the object that is applying the force is gaining energy. Here is the fourth practice problem. The solution will come in 3, 2, 1. So the work done is the final gravitational potential energy, which is mgh. 200 newtons is the force of gravity, and the force of gravity is m times g. So then we also know that the height is 20. So now we can plug in all the values to get that the work is 4,000 joules. Here's the fifth practice problem. The solution will come in 3, 2, 1. Here's a diagram of the satellite orbiting Earth. So its velocity and displacement vector point in the same direction because the satellite moves in the direction of its velocity. And the force of gravity points perpendicular to the velocity and displacement vector. So the work is equal to force times displacement times cosine of theta. And in this case, since the two vectors are parallel, theta is 90 degrees and cosine of 90 degrees is 0. So the work done is 0. Another solution is that the satellite maintains a constant tangential velocity, so its kinetic energy doesn't change, and the distance between the satellite and Earth is always the same, so its gravitational potential energy doesn't change either, and its total energy doesn't change, so 0 joules of work is done on it. Here's the sixth practice problem. The solution will come in 3, 2, 1. So you set the final kinetic energy to the initial gravitational potential energy, and you have mass on both sides, so you can just cancel that out. And now we're left with just one unknown, which is g, and you can solve that g is equal to approximately 0.78 meters per second squared. The second solution is to use the fifth kinematic equation. You know that the final velocity is 5, the initial velocity is 0, and the distance it has traveled is the height, which is 16. And you can solve to get that the acceleration is 0.78 meters per second squared. Now we're getting into power, which is work done over time. The formula for power is work over delta T. The units is watts. And be careful because W represents both work and watts. So you need to make sure whenever you see it, you know which one it's supposed to represent. Usually, if W is placed after a number and there's a space between the number and W, it represents watts. Otherwise, it represents work. So we can manipulate the power formula. We know that the work is force times displacement times cosine of theta. And using one of the kinematic equations, we can change delta T to d over the average velocity. So then we can simplify to get that power is equal to force times average velocity times cosine of theta. So remember these two formulas. Power is equal to work over time, and power is equal to force times average velocity times cosine of theta. Here's a practice problem for power. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So for part A, the kinetic energy in the end is the work that has been done on it. So we can plug in all the values that we know to get that the power is 2.25 watts. For part B, we use the second formula for power, and the force and displacement are in the same direction. So we can just ignore cosine of theta, and we get that the power is 15 watts. Here's the second practice problem. The solution will come in 3, 2, 1. So we use the second formula for power, and be careful because the force is not 1,000. The formula for the force of gravity is m times g, so we also have to multiply it by 9.8, and then we can use the formula for power, so force times average velocity, and we get that power is equal to 49,000 watts. Here's a third practice problem. The solution will come in 3, 2, 1. So the amount of work done is equal to the kinetic energy at the end. So power equals kinetic energy over time. Now you can plug in all the values. Be careful because the power was given as 25 kilowatts and you need to turn that into watts. You can multiply both sides by delta T and divide both sides by 25,000 to get that delta T is 240,000 divided by 25,000, which is 9.6 seconds. Now we're getting into the final topic for this video, which is collisions. Let's suppose that a 10 kilogram block moves towards a 5 kilogram block at 9 meters per second. After they collide, what will the velocity of each block be? In the previous video, we talked about inelastic collisions, where the two objects stick together after they collide. Now we're going to be talking about elastic collisions, where we assume that no energy is lost as heat or sound due to friction or when the blocks collide. So we know that momentum is conserved and energy is also conserved. So to solve this problem, we have to calculate the total momentum before the collision, which is 10 times 9 plus 5 times 0, which is 90 kilograms times meters per second. And the total energy before the collision is 405 joules. So we set the velocity of the 10 kilogram block after the collision as x, and the velocity of the 5 kilogram block after the collision as y. So the total momentum after the collision is 10x plus 5y, and that is equal to the momentum before the collision, which is 90. And the total energy after the collision is 1/2 times 10 times x squared plus 1/2 times 5 times y squared. And it is also equal to the energy before the collision. So now we have a system of equations. And solving this system of equations gives that x is 3 meters per second and y is 12 meters per second. Solving this system of equations can be tedious, but if you have a tool that is needed, it can be easily done. By using the Desmos graphing calculator, all you need to do is find the intersection of graphs. So type in the system of equations. And you will see that these two graphs have two intersections. The first one is the pair of velocities before the collision. That's not what you want. This one is the pair of velocities after the collision. So this is how you solve this system of equations. If you can't use Desmos, you can solve using substitution. So starting with the equation for momentum, isolate one of the variables. In this case, we're going to isolate y. And then plug in the value for y into the other equation. After simplifying, you can get it down to a quadratic. You can solve this quadratic using any method to get that x is equal to 3 or 9. We're ignoring 9. And then plugging in the value for x into one of the equations gives that y is equal to 12. Here's a practice problem. Feel free to use Desmos. The solution will come in 3, 2, 1. So the total momentum before the collision is 1 times 3 plus 1 times 2, which is 5. The total energy before the collision is 6.5. And we're using V1 and V2 to represent the unknown velocities after the collision. So we have this system of equations, and solving will get that V1 is equal to 2 and V2 is equal to 3. In fact, whenever you have two blocks of equal mass collide and they're traveling in the same direction, their velocities always switch in order to preserve the momentum and energy. Here's another practice problem. The solution will come in 3, 2, 1. So you have to be careful with the signs because the two blocks are traveling in opposite directions. So you have to set one of the velocities to negative. So you're going to get that the total momentum before is 30 or negative 30. The total energy before is 225. And then the total momentum after is 4x plus 2y. And that's equal to 30. And then you have another equation for the energy. And then solving, you'll get that x is equal to 0 meters per second and y is equal to 15 meters per second. Since the problem was asking for the speeds, if either of those two results were negative, you would have to change the sign. I hope this video was really helpful. We're getting near the end. There's only one video left. In the next video, you will learn about the last concept for this course, which is spring motion. Springs are unique from anything we've learned about in this course because, as you'll see, the force and acceleration are not constant. And throughout this entire course, we've been dealing with constant force and acceleration. So it's going to be interesting to check it out. Thanks for watching. I'll see you in video number 9.